homework, which is due next Thursday. From now on, the homeworks will get a little bit more applied. I mean, of course, you have to do some calculations. There is always, I like to give some problem to figure out. So there is one problem which has very simple solution, but I mean, there is something that you have to figure out on that homework too. But I think that's the idea. I mean, you get some exercise in just finding non-trivial solutions. So the homework is 4 problems for this week. But again, right now, don't think about the homework. I mean, just do some preparation for the exam. Go through the formulas that we have studied and so on. Again, we're meeting in Riddick, not here, for the next lecture. So for the distance education students, there is not going to be a lecture on Thursday. We'll continue next Tuesday. Okay, what do we have the lecture for today is optical effects and microscopy in colloidal systems. But before I start that, actually, I have to finish. First, we have to finish a few slides from the previous lecture, just because to finish off with the dipole-dipole interaction. I want you to have these formulas and understand what's going on here. I want to stress 2 points have been somewhat unclear. One is how to calculate charge of protein molecules. I mean, I have received an immensely diverse array of questions about that, so I'll go do a little bit of reminder about this. Then some people were obviously overwhelmed by this problem from Mizushvili with the many solutions about which is important what. This is not so much important to the test, but I'd like you to think in terms of colloids, so we can go through that too. Just to finish here, if you remember, we have been discussing what happens when the dipole moments of the particles interact with the field that causes them. Now, we also discussed that when you have, okay, this is not going to write, so I have to use the mouse. So we also discussed that when you have 2 particles nearby, the dipole moments in these particles are also going to interact between themselves. If you remember from our discussions on van der Waals forces, the strongest interaction between dipoles is when these 2 dipoles are in line, which comes to tell you that the particles are going to organize themselves in lines. The dipoles kind of organizing each other, facing each other in line. Now, if you remember, this was the formula that we derived then for the interactions between 2 particles in line. This was the formula which we derived on the previous lecture for the dipole moment in a particle which has been caused by the electrical field. So we're going to have these 2 particles, each of which is going to have this moment. So what we could do is we could put in this moment. Now the question is, what is the distance here between the 2 particles? And obviously the strongest interaction is going to be when the particles touch each other. So the distance between these 2 particles is going to be 2 times their radius. So we put everything together in this formula. We obtain the formula for the energy of interaction between 2 particles with induced dipoles in the field, in a chain of particles. Then we usually work with force when it comes to dielectrophoresis and alternating fields. So we can take the derivative of this function, and this is the expression which you obtain for the force. Now, you're not going to find this expression in any textbook because actually I derived it as a part of just continuing the class here. What you have to focus on here is, first of all, this force does not depend on the gradient of the field, it depends on the field itself. This coefficient here actually takes into account that actually when you have 2 dipoles being so close to each other, the interaction is in a way amplified because they really face each other. You can think of the counter-ionic atmospheres merging, you can think of the charged sides facing each other and so on. So in reality, the interaction is usually stronger than the theory. And you also have a chain of dipoles interacting with another dipole. So particles in a chain interact between each other more strongly than 2 particles separate from the chain. So in the chain, just because you have a chain, the interaction can be enhanced significantly. This is an experimental image of chains of particles, which has been obtained by Simon Lumsden. It's part of our research. You can see that they really form very nice straight chains along the direction of the field. And finally, one application that has not been discussed too much in colloid science, but is very widely used in rheology, and is very important for a few applications, are the so-called electrorheological and magnetorheological fluids. Now, viscosity is certainly not the most beloved topic for many people here, but imagine that you have a liquid with particles, and you apply electrical or magnetic field across this liquid. The particles are going to chain because of the dipole interaction. So what happens is, if the field is sufficiently strong, you're going to have this chain of particles interacting, kind of bridging the gap between the two surfaces with liquid. And this is the basis of the electrorheological and magnetorheological effect, which people use in many applications, including, for example, one application would be in expensive cars. We're going to check out how you can change the properties of the windows by electrical field and particles. You can also change the properties of their shock absorbers by applying electrical field. So depending on whether you'd like more hard drive or more soft right, you can change the rheology of the liquid inside the shock absorbers. But of course, there are other useful applications too. And people have found experimentally that the shear stress changes with the squared field intensity. And the formula that I just derived on the previous slide, you can see how actually the interaction between the particles affects the rheology. There are some things to be known here about the constants that are involved and so on, but you can see how, as a function of the field intensity squared, you can change the rheology of the liquid. And again, don't ask me why this arrow faces outwards, just because it's kind of tough to show an arrow faces in the other direction without confusing the forces. We have three types of electrically driven particle motion. One would be, this one would be what? Towards the electrode. Would be caused by what component of the field?
Okay.
I have combined here, like, just read the title, electrophoretic plus dielectrophoretic. Right. If you, let's say, if a particle is positively charged and you apply negative potential on that electrode, so the particle is going to move towards the electrode. If you don't apply any constant potential, but if you apply alternating field, you can move the particle in the gap or out of the gap, depending on the frequency. And finally, if we have two particles in the gap, these two particles are going to attract each other because of the chaining force. And all of this gives you very large possibilities for manipulating colloidal suspensions on chip, and we'll discuss this a little bit later when we go to the different types of applications. Some of it is you're going to tell me about some of this on the next discussion, actually. Okay, any questions?
What's the scale of that?
This has been taken with 1 micrometer particles. So each particle is 1 micrometer. So we can observe them easily by microscope. It's a very nice experiment, and I hope I'll be able to tell you a little bit more about this in the later lectures.
But you would expect it's dependent upon R squared. So is there a limit to how large these particles could be before the chain effect?
Well, the larger the particles, the easier, because
So I want to see smaller particles, though.
when you go to small particles, other effects come into play, as we have in the microwires. So they start assembling collectively rather than as a chain. So one of the discovery, which is actually part of my recent research, and Ketan here is working actually on pushing this boundary further, is the discovery that you can have very small particles and you can still aggregate them by the electrical field. These are our microwires. As long as you can have attraction, you can aggregate them. So there are a variety of effects there. Of course, when you go to smaller particles, the chaining, you have potential to induce chaining. Okay. Let's move to the other lecture. And I'm going to tell about optical effects, microscopy. It's really fun. And lots of beautiful images and movies. Before that, because we have the exam and I really wouldn't like to leave elements that you haven't understood well. Now let me again walk you through the procedure for calculating the charge of protein molecules. You have two types of group on the surface. The first type of group are groups which which actually release hydrogen ion or proton and form a negative charge on the surface, acidic groups. The second type of groups are groups which actually bind the proton when protonated, and in this way, when protonated, they have a positive charge. So that's where the positive and negative charge groups come. Now, these are the expressions for the number of charge groups, the total number of groups, pH and pKa. pKa, if you remember, was the constant, the equilibrium constant of this reaction. And as you can see here at pH equal to pKa, this is going to be 0. 10 to the 0th power is 1. You are going to have 1 plus 1 here. The total number of groups divided by 1 plus 1 is half of the groups. So at pH equal to pKa, half of the groups are going to be charged, half of the groups are going to be uncharged. This is kind of the physical meaning behind pKa. And of course, when you change pH in one or the other direction, more groups get charged or uncharged. Now, in order to calculate the total charge, you have to do the sum. I had made some errors in the indices when I had written this equation first. This is the exactly right indices. You have to sum over all positive groups. Each group multiplied by this term here, pH minus pKa. And then you have to subtract here the negatively charged groups, again like in the same expression. Now you have to subtract this here because negatively charged groups have obviously negative charge, right? So the charge of the protein changes from negative to positive, and then there will be some specific pH where the charge on the negative group is going to be approximately equal to the charge on the positive group, and this is the isoelectric point. Now when you calculate the charge of this protein, you have one terminal amino group, one terminal carboxyl group. You don't have any intermediate groups here on the chain. I mean, these groups have already been formed as a part of the peptide bond. And then each amino acid has this side group, one per amino acid, which depending on the amino acid can be charged. I have given you these groups in the table. So by knowing what type of amino acid, you have to sum up over all the amino acid groups which stick out of the chain and the two terminal groups, and you get the total charge of the protein. And when you do this calculation as a function of pH, you calculate the charge of the protein for all the pH region. You can see where it's going to precipitate, close to the isoelectric point, and so on. Okay. Any questions here?
In the solutions that are going to be handed out, it's going to be clear how they got the pKa values for the ones that have left.
Frankly, the solutions that I have are based on a program which one of my postdocs had made some time ago. Now, if you like, I can send you the program actually, and you can check out the equations that have been introduced in the program. Otherwise, you're going to get the full solutions like as values over the pH value. If anybody who like, who can get the program and can check it out. I mean, it's an Excel spreadsheet.
What was your question?
Whether we're going to, in the solutions, we're going to see exactly how this has been done for the problem at home, right?
Yeah.
How the pKa is calculated?
Well, for like two of those, like the two of those, there was no N group. Like it was both the. Confused.
Well, there's always N group, right? I mean, like the first problem was eventually you had to figure out that you only have two N groups. and you don't have any charge groups on the peptide chains. That was the first problem, the one where we have only neutral amino acids. I know that this problem has been confusing, but it's confusing because of its simplicity.
Peptides are the yellow.
Well, an amino acid here would be,
There's 2 amino acids.
this is a 2 amino acids bound together. So this has been one group from one amino acid and another group from another amino acid. We can join them together. You have released water out of here. So this amino acid is actually kind of like these two groups have formed a bond. But you always have one negative and one positive groups on the end, and that's it. So even if you don't have side charge groups, you're still going to have one negative and one positive group.
So the pKa's came from the nodes.
The pKa comes from the pKa. I've given you the pKa's of all groups which you need to know.
Yeah, some didn't
in the
have
nodes.
side group PKs. They just had
Right. The side groups
So
pKa, you
like-
have to count how many molecules with a
Or
certain
in
side
that-
group you have.
With that pH, how many are in that condition? And
Right,
how many
right,
are the other?
right.
Okay.
So, yeah, but like alanine and glycine just have a
Anyway,
hydrogen.
if you'd like to get the program for calculating pH of pK and the isolated point of proteins and the charge of protein, it's an Excel spreadsheet. I can give it to anybody who would like to take this practical example. You can see the formulas.
That's separate from the homework where the pKa wasn't given in the problem statement. That was actually in the notes, but it was like a given.
Okay.
So-
Okay,
Yeah,
let's,
okay.
yeah, we have to move on. Let's discuss this after the
That
class.
formula is different than the one that at least I used for the homework.
I had made some mistakes in the indices when I gave to you.
Okay,
Um,
that was taken into consideration.
Yeah, which may actually reverse your charge, your charge that you obtain, but I mean, like as long as you have done the calculations right, you're going to obtain the inverse charge, but you're going to obtain the right number, which will take into account when you create homework. Don't worry about that. Okay, one other problem that has caused lots of confusion as question is the problem 12.5 from Izrevashvili, which says why positively charged divalent counterions are better coagulants or flocculants. So, oops. This was a homework problem and people were asking lots of questions. So we have two negatively charged particles. One here and one here.
Is this the true-false questions?
Right. So you have a divalent counterion, and the question is why this counterion would be much more effective than a single counterion, a single valent counterion. Now you can think of this as being sodium ion, and you can think of this, for example, with calcium ion. And you know that when you make cheese, you put what inside the protein to precipitate it? Calcium, right? I mean, there is no chance of getting cheese if you put just sodium chloride, if you just dump in salt. But if you dump calcium chloride, the protein precipitates. So the question was eventually which true or false is true for two valent counterions. The first one is they screen the electrostatic repulsion better. I think this is obvious that they screen the electrostatic repulsion better. The second one says they are more hydrated. Well, I mean, like how would the hydration per such account for the attractive force?
Oh, what? The divalent ions are more hydrated than the...
They are more hydrated, but why are better coagulants or flocculants are not really rated to their hydrated state?
I got that part wrong.
You understand that the hydration of water molecules around actually is going to keep the particles apart, right? So they're more hydrated is not really true answer.
So there's oscillation forces there?
Yeah, I mean, we'll come to that later. Well, the oscillation forces, yeah, which are going to be repulsive.
Yes.
The water molecules wouldn't like to get outside the kind of, to get separated from the counterions. So the second one is false. Hydration really doesn't help in terms of electrostatic coagulation. They bind more easily and hence lower the surface charge more easily. True. I mean, if you have charges on the surface, then obviously when two charges bind together to a charged surface, they would hold much more strongly than a single charge. So calcium ion really is going to bind to the surface more strongly. Now, the next two are actually very similar. They have additional ion correlation attractive forces, and they can bridge to surfaces by virtue of having two charges. True or false?
False.
True.
There's actually a later chapter goes into the correlationary force.
Yeah, so eventually you have a negatively charged surface here, and another negatively charged surface here. And if you have two positive charges in the middle, you're going to get bridging.
How do you not just double layer repulsion reduction?
Because now you are already thinking about kind of on a molecular scale what is going to happen. Now there is no way you can put a single plus charge and have bridging, because a single plus charge is still not going to suppress these two charges. But a single two-valent ion can bridge the two negative charges if it happens to be exactly between them. This is also what is called ion correlation attractive forces. So the position of the ions are in effect correlated. So it's not just here, it's somewhere. It's right on top of this charge and right on top of that charge. Obviously, if this charge is here, I mean, it wouldn't bind them and there will be no force. But imagine that the surfaces can adjust a little bit and the calcium ion just bridges them between. And this is an effect which has been measured really in practice. They can disrupt the water structure more effectively. False. They may disrupt the water structure, but this is hydration repulsion. They disrupt the water structure in the sense that they attract water. They have a lower kinetic energy. Well, I mean, have you ever heard me discussing the concept of kinetic energy of ion in terms of flocculation and coagulation? I mean, like, it's really, I mean, false. I mean, like, it does not have much to do with in this case.
What's the question?
They have a lower kinetic energy.
Wow.
How does the kinetic energy of an ion? No. Okay.
I mean, they're going to get slower, but
Okay.
also everyone back.
Okay, let's keep up. They dehydrate surfaces on binding to them. True or false?
False.
No, actually, the answer from my viewpoint is true.
Shouldn't they hydrate the surfaces on binding?
Well, they would hydrate the surfaces if they bind on a surface which has not been hydrated now. However, we have positive charges binding to a negative surface, right? And originally both the surface and the ions were hydrated. But when you bind them, then the net charge is zero. Water molecules wouldn't like to be, I mean, like it essentially becomes electroneutral and releases water molecule which has been bound by the ions. So the hydration is going to oppose this process, but once they bind, they get dehydrated, and this promotes interactions, binding. And the last one is connecting to this one. They enhance the hydrophobic attraction. Obviously, if the surfaces do not have charge, they get to be hydrophobic, and binding is better. So now, I don't claim that this is 100% correct, and other people may have different opinions on some of these topics. But I mean, essentially, these are experimental facts which I know from calcium studies on protein precipitation. You can see that there are a variety of effects which are complex, especially when it comes to hydration. We discussed that in the lectures. And these effects can be very strong and sometimes very important. So that's why I wanted to go back, and this is in a way kind of a review of hydration forces, oscillatory forces and so on. Do take a look at those forces. You may work on them qualitatively, but I still may ask you some quantitative questions on the test, for example. So think about these forces. Daniel.
Did you mean quantitatively? Did you ask us number questions?
You can't quantify such forces easily, but you can qualitatively, you can still think about how they're going to work.
So the hydrophobic forces will arise from a non-charged surface.
Right. Hydrophobic forces, if you remember, are ones where water would like to be expelled from out of the hydrophobic surfaces so they can come together. So, okay.
Yeah, you just said that for milk, for coagulating the proteins in the
Right.
milk, we need CO2
Calcium.
plus, calcium instead of sodium.
Right.
But if we add like a lot of more amount of sodium, wouldn't and even for these points, wouldn't it be the same effect? Like,
Well, it would be the same effect, or it would be similar effect.
yeah.
But
It'll be healthy for you too.
You'd have to add like 64 times as much.
Probably
Right.
no, but for these,
you have to add enormous amount of sodium, and it doesn't work that well. Actually, for protein, calcium really promotes binding and unbinding of the proteins together. So it's even more than 64 times more effective than sodium. So in this case, I mean, you cannot add in salt and salt and salt, and nothing much happens. You adjust a little bit of calcium. How much?
I don't know, but basically you have
Some millimoles.
phosphate groups.
You also have phosphates, which work in the same way for the opposite charge groups. Phosphates actually binds to, because proteins have positive and negative groups, right? So calcium phosphate is the one that's used to precipitate proteins. Calcium ions are multivalent ions which suppress negative charges. Phosphate ions are multivalent ions which suppress positive charges. But I mean, you just add some millimoles and it goes down. Well, if you have to add sodium chloride, I mean, you have to dump and dump and dump. Typically, proteins precipitate at some values of sodium chloride which are on the order of moles, which is a lot. I mean, 10 times more than in the blood, for example. So you wouldn't like to eat that cheese afterwards. Okay, let's finish with this part of the lecture, move on to the next one. Now, I usually begin with some nice picture, but this time I'm going to begin with something more boring, just because I'm going to show lots of pictures afterwards. I just want you to kind of like learn a little bit more first about reflection and interference, which are important for all cases where we have colloidal systems. And then I want you to just walk you through different types of optical microscopy systems useful for studying colloidal suspensions. Now, I won't be able to give you all the details. I just want to give you a flavor of the power of optical and electron microscopy for studying colloids. And I also want you to understand how important it is to use different optical methods rather than just putting it into the microscope and trying to see something. You have an enormous variety of tools which you can use in order to see the systems better and to characterize them better. Now, every phenomenon in colloidal system would begin with reflection from a surface. This is something which we're going to use a little bit later. Just a reminder of the physics of reflection. You have a beam which falls down, one that's reflected and one that's refracted. You have a variety of very simple relations which get to be more complex when you go deeper into physics. You have, usually when you work with beams, you work with the electromagnetic field intensity rather than the power of the beam, which is the intensity squared. The field squared. So the field that is going to be reflected is going to be the falling field times the coefficient of reflection. The field that is going to be transmitted, okay, this is the transmitted field, this is T here. The field that is going to be reflected is the same times the coefficient of reflection. Obviously, if you take the reflectance and the transmittance, which is the squared, now the intensity is the squared field. The reflectance and transmittance of a sample are the squared coefficients of transmittance and reflectance. Obviously, in a system which does not have adsorbance, like most of the colloids, you are going to have these two being equal to 1. So no light is lost, some of the light is reflected, some of the light goes through. Now let me ask my favorite question here. You have latex. Now latex is polystyrene. It does not have absorbance. No light is lost in the latex on reflection and transmittance. Now why does this then the latex look white rather than transparent?
It's a more
latex microsphere in suspension. Just microspheres around in suspension.
Amorphous would make it clear anyhow.
Hmm?
Amorphous would make it clear anyhow.
Yeah,
What are
okay,
you
yeah,
talking
that's,
about?
but I mean, like amorphous is a concept from solid state
Yeah,
science.
good point.
Right. So why does
Like
transparent microspheres in transparent liquid look milky, white? This is something that we're going to study in a bit more detail later.
It's called the Tyndall effect.
Yeah. But I mean, what's the effect? Well, where it does come from? Right, it comes from, okay, diffraction is about, right? It comes because these microspheres reflect, refract light and scatter it. So the beam can never go straight through, it just gets scattered and refracted and reflected through the particles.
But if they had the exact same index of refraction,
Well, sure, but I mean, you can see this here because the coefficient of reflectance is actually can be immediately calculated from the refractive indexes. The cause of the refractive indexes, this is going to be 0. So if you match the refractive indexes, you're not going to have any reflectance. Like some authors of science fiction can assume that you can do for a human body and so on. Theoretically, if you can adjust the index, you're going to be invisible, right? Now, how we're going to do this is another matter. But I mean, in principle, there is a theoretical possibility like that. There is, of course, the Snell's law, which relates the angles of reflection and refraction. So these are very simple formulas. Now, something that I want you to illustrate for exactly how you can use such measurements of reflectance in colloidal systems is thin films. If you remember when I showed you these foam films, they had these dark spots, they had these nice colors and so on. And this is like an immediate method for measuring interactions on a molecular scale by using light. You have a very thin film and you measure the thickness of the film. I won't derive everything here, I just want to give you a flavor of how this is done. You have a falling beam on a film. This beam, some of it is going to be reflected from the top surface. Some of it is going to be reflected from the bottom surface, and some of it is going to go through. Think of this as a foam film. The one that gets out of the film may be reflected again, but sooner or later is going to end out. And you can see that the distance in the paths here of each beam that exits in this direction, in reflected direction, is the same. If the film is perfectly plane parallel, then this phase difference is going to lead to interference. The coming beam can either be stronger than a single reflected beam, or they can be weaker, They can self-enhance or they can self-cancel. The formula which gives you the dependence between the intensity of the reflected light is here. Coefficient R, reflectance, is the squared coefficient of reflectance from the previous one. I0 is the intensity of the original beam. And here you have cosine theta, where theta is the so-called phase difference. It is dependence on the wave number, k, which is simply 2 pi divided by the wavelength, and the phase difference, which is just a certain number, which is usually pi, if you have reflection from a surface with high refractive index. Now, this d distance here, optical distance, is 2 times the wave number, the thickness of the film, and the cosine theta of the falling beam. So, kind of to make all this simple, if you have a certain film, if you measure the intensity of the reflected light, if you know the intensity of the falling light, if you know the wave number, this is the lambda, if you know the thickness of the film, and if you know, of course, you know how many surfaces you have, you can calculate the thickness of the film. So the only thing that you don't know here is h. This lambda is going to depend on the refractive index in the film, because lambda changes with the refractive index. Now again, I'm going to skip some derivations and just give you the basic formula, which can be important in any types of measurements, which relates, in this case you can normalize it. Actually, you can use the maximal intensity and the minimal intensity, in case you have some. So if you can measure the delta x, kind of like where you are between the maximum and the minimum intensity, you can calculate the thickness by this formula: lambda divided by 2 times pi, the refractive index of the substance in the film, arc sine of the squared, this parameter. And just to make the matters a little bit more complex and more interesting, you know that interference is a kind of oscillatory phenomenon. So if you plot the film thickness and the relative intensity that you're going to get, so we have zero intensity at zero thickness. It goes up at some thickness which is equal to 1/4 the wavelength divided by the refractive index. You have a maximum intensity. It goes down, then up again, down again, and so on. If you do this for 2 different wavelengths, you're going to find out that the maxima of the reflected light are at different wavelengths. And you have this phenomenon, not so much these days, but previously when the cars were leaking some oil. What can you see on the surface of the roads after rain? You can see those colored fumes of oil. This is because, no, this is not because of, this is because of interference in the film. This is because, let's say if you have a film which is this thick, it's going to reflect red light, but the green light is not going to be reflected at all. And you can relate the thickness if you know where you are. You have 2 parameters here, L, which changes from 0, 1, 2, and so on. And you have this sign which can be plus or minus. In order to know where you are, I have plotted here L is equal to 0, you use plus. This is for this region of the curve. For this region of the curve, L is equal to 1, you use the sign minus. For this region of the curve, L is equal to 1, you use the sign plus, and so on. It's a very useful formula which you can immediately use to calculate thickness or distance between colloidal objects, if you can measure the reflected light. Now, Shalini had a question.
Yeah, why isn't there a bending of light, ray of light inside the thin
Why
film?
is it what?
Why isn't the ray of light bending inside the thin film?
Bending?
Over here? Would it just go straight?
Yeah, it's, what you say here is that why this angle here is equal to this one.
Yeah.
In reality, it won't be. I mean, there will be some small difference. I mean, it's not shown here in this picture. I mean, you are right that if you follow the laws of physics, I mean, this angle here should not be exactly equal to this one. What I have shown here is this distance here, actually this d, accounts for, this is the distance between the two beams, actually, the optical distance between the 2 beams. This is the phase difference. This is the distance that this beam travels more compared to the other one. You have, the beam comes here and gets reflected. Then this beam comes here, gets reflected from the other surface, and then comes out of here, and then interacts with this beam. Now the distance between the 2 beams is essentially this distance here, which actually gets into account in that formula. That's how it gets calculated. This is the phase difference, which comes because the 2 beams travel different distance. One gets reflected from the first surface, and the other goes to the second surface and then gets reflected. Any other questions? I'll give you immediate examples of how you can use these formulas for different types of measurements. Okay, I've given you a couple of problems which would allow you to do some thinking here, and certainly are going to involve questions of the application. This formula is really very simple. You just have to figure out what is the thickness, which parameter, which number L you use, and which number, whether you have plus or minus. But it's a very simple formula which will allow us to relate the thickness, wavelength, refractive index, and reflected intensity. Let me show you some examples because, I mean, obviously, theory alone doesn't help here. Let's start with the pictures. You have a bubble which you press against a thin liquid film on a glass surface. If you illuminate this with monochromatic light at some wavelength. This is what you're going to see. That's how your film is going to look like. Dark, white, and so on. And you know already from the previous slide what these thicknesses relate to, the maximum of dark intensity and bright intensity. So this actually allows you to know the thickness here in the film. You can say in this position the film is lambda over 4 times the refractive index. In this thickness it's 3 times lambda over 4 times the refractive index and so on. So you can actually, this actually allows you to reconstruct the profile of the interface and allows you to measure the thickness here. So from an experiment like that, you just press a bubble, you illuminate, you measure this optically, then you can get the contact angles, the repulsive forces, because you're knowing to go how thick the film is, so I can calculate D of O. You can calculate the film thickness, and you can measure the film thinning dynamics. You can see how the film thins down hydrodynamically. You can do the same for foam films. This is actually something, I have done something like that for emulsion films in my graduate research. You can put some liquid inside a capillary, and when you suck the liquid, the two surfaces are going to meet. They are going to form a thin film, and when you illuminate this film through a microscope, again you are going to see these rings which tell you how thick the meniscus is. You can measure contact angle and you can measure film thickness. What's more, you can measure film dynamics. This is actually from a paper where I'm a collaborator. This is actually a thicker film in the middle, which falls out. You have a plane parallel thick film, which is bright. And then this film thins a little bit further. And then suddenly you see those spots. You see a jump-wise transition from a thick film to a thin film. So the film is either thick or thin, and then the thin film spreads out and occupies the whole area. Now, again, question for kind of fast thinkers. Why does the film has these two stable thicknesses of a thick and a thin film? With relation to all the theory that we have studied so far.
Because of the surface energy?
Well, that's why do you have two stable positions? Kind of think about something that we have studied. I've been showing you this at least two consecutive lectures.
Is it like when you were talking about earlier where the oil would evaporate, and it would cause it to come back together, then it would get used to itself and
No, that's a dynamic effect. No, this is a thermodynamic effect. Now, the effect like that is here when you have these lenses and so on. This is hydrodynamic, but what I'm talking is about thermodynamic effect, in which case, which colloidal theory tells you about two different stable states. Oh, yeah.
Is this a soap film?
This is a soft film with negative charges on the surface. But if you remember, D of O theory goes like that. I'm going to draw here. Repulsion, deep attraction, repulsion, small attraction, too far away to have any force. So if you have two charged surfaces, if you remember, the two charged surfaces can stop here, or they can stop here when you press them. Or actually the equilibrium state is going to be here, right? So this is exactly, you can immediately see how you can see the two minima in the D of O theory. Long range electrostatic repulsion and short range van der Waals attraction combined with steric repulsion. Here just the film doesn't break because the surfactant chains are pressed towards each other and don't allow the two surfaces to meet. But it's very thin. It's so thin that if you go back to the diagram, it's somewhere here. It's very, very thin film. So very small thickness, very thin film. So this is the so-called black films. If you remember when we were beginning this class, I showed you this nice image of a salt film which had these black spots inside. And I ask you why does it have black spots? And why doesn't it reflect there? And now hopefully you know about this.
Actually, yes, is what it is.
Huh?
Yes, is what it is.
I asked you what the film is, but then I asked you why does it have black spots? Now you know that it has black spots because it can jump to the deepest minima in the van der Waals curve. So the two surfaces are very, very close to each other. And when the surfaces are so close to each other, by the formula of the reflectance, you get zero reflectance. This is what is called black film, common black film. Okay, that was about, this is the formulas that I want you to study for there. Now I'm going to go to some nice microscopy images. But now is the time to ask questions if you have any. We're going to now, we have begun optical phenomena. We're going to study scattering and diffraction later, including light scattering, of course, which is a major matter. But now, let's go to kind of just some practical issues. Now you want to observe a colloid, and what do you use? A microscope. So I want you to walk through a variety of microscopy techniques. Again, maybe you're not going to remember everything now. But what I want you to know is that you have lots of power by just combining the way you observe the system. Before that, however, a microscope, what do we have in a microscope? You can actually take some tutorial on microscope on Olympus, has a very nice website. You have the illuminator. The light goes through an optical system which focuses on the sample which is here. You have the objective which observes the system. You can observe it with your eye, or you can let it go straight to some kind of video or digital camera. Now, which is the most important element of that kind of, the one that determines the quality of the image that you're going to get out of the microscope?
Numerical aperture.
Of
The lens.
which lens?
The lens.
The black one.
You mean the objective?
Yeah, the objective.
Okay, right.
The overall.
Right. Kind of, I mean, there are two. First of all, like the most important actually optical element, and the one which determines what you're going to see, is the objective, the objective of the microscope. And I'm going to tell you exactly about the objective on the next slides. The other important thing is how you're going to illuminate your sample. Typically, you assume that if just light falls on your sample, you're fine. But you're going to see that this is not the case at all. The illumination determines what you're going to see. The objective determines how well you're going to see it, how fine, at what resolution, and so on. Just a little bit of theory. How do you determine the resolution of an objective? Why can't you put any objective here in the microscope, and then you can put lenses here and magnify, and you're going to see atoms, right? If you put more lenses, these lenses magnify, right? So what is the problem with seeing some very small features, even if your objective lens is not that great?
Physically can't see it.
Yeah, it's actually a bit more complex. Now, theoretically, now what happens when you start magnifying an image? Now, if you can imagine that you have just a single spot. Now, every time you look at this spot through optics, you're going to see that the spot actually has this diffraction pattern around, kind of smearing around the spot. You can never see the edge of the spot as perfectly like a transition from a spot to background. You're always going to have this diffraction pattern, which is determined by the microscope and the lenses. And the lowest resolution that you can see is actually the case where these two diffraction patterns merge. So if you have two spots, maybe this is the final position of the spots where you can resolve them. But if you go here, you already see one spot, because the diffraction patterns around them merge. Now, what determines how well you can resolve two spots? This is the resolution of the microscope. This is the smallest feature that you can see on the microscope. It is determined by the numerical aperture of the objective. It's a parameter for every objective. And now there are two formulas depending on whether this is like a fluorescent particle which emits light or whether this is an illuminated particle. Generally, this is kind of a good formula just for estimates. The resolution here is equal to 1 times the lambda, the wavelength, divided by the numerical aperture. So if you want to have high resolution, you want to do what? Right, I mean you're going to increase the but a little bit. I mean you can see that this difference is not that great. This is the what's important. Typically this won't be about that, so I mean like these formulas are very similar. Now, you work at smaller wavelength. The smaller the wavelength, the smaller the higher the resolution, right? You want this to be small. The smaller the resolution, the smaller the features that you see. So you can work at smaller wavelength, or you can work with objectives with higher numerical aperture. Now, how about the wavelength? Now, how can you relate the wavelength to something that we're going to study a little bit later in the lecture? Right. Right. I mean, obviously, with visible light, you're restricted to a range of wavelength which is small. The wavelength of an electron, however, is much, much smaller than the wavelength of light. So that's why electron microscopy actually allows you to resolve much smaller features. So the smaller the wavelength, the higher the resolution. Now for optical microscopy, you have the numerical aperture. Now the numerical aperture is actually determined by the refractive index of the media and the angle at which the objective looks at the sample. The higher the angle and the higher the refractive index, the higher the numerical aperture, which is not good. I mean, it's good, of course, but it's not pleasant.
You have a very low depth of field.
Right. So the higher magnification your objectives, the closer they get to be to the sample. The closer they get to the sample, the higher the probability that you can do what?
Smash your sample.
Yeah, smash a sample, or if you are like really unlucky, smash the objective, right? And then the other unpleasant element is that some objectives at high numerical aperture, in order to increase the numerical aperture additionally, you want something with high refractive index, which is an unpleasant oil, which then you have to wash off the objective. And this is just an example of what you see of an objective. Magnification. Now you know, however, that it is not the magnification which determines the smallest features. It is the numerical aperture, which is shown here. So it's magnification 60 times at a numerical aperture of 1.40. This is a very high numerical aperture, and it is very high because, as you can see here, this objective needs oil. You have to put a droplet of oil below the objective and between your objective and your sample. If you don't put a droplet of oil, then you can really try to focus hard, and you're going to see some very unclear images. And then, I mean, don't blame it on the microscope, of course. I mean, I've seen that. I mean, if it says oil, this means that this is designed to work through oil. And you have to put, otherwise it just won't focus properly. You're not going to. So these are things. Now here, this is related to the tube length and working distance. The working distance in this objective is 0.21, which means that it's almost millimeters, which means that it almost has to touch the sample. If you have a cover glass slip, which is of the thickness of 0.1, 0.15 millimeters, this means that you have to adjust your objective to be 0.07 millimeters away from the sample, or otherwise you can smash it, and you're not going to see much. So this is the backside of having high resolution optical microscopy. But you need to be aware of those things. And again, the feature of the objective which is most important is the numerical aperture. You can have high magnification, but if you don't have high resolution, you're not going to get the small features. Okay, questions so far? Let's go then through different types of microscopy. Now, you have chosen your very good objective. The next thing that you have to think about is illumination. The simplest illumination is, of course, when the light goes directly through the sample. But you have noticed that in many cases, this just leads to blinding bright field and you don't see much. Especially when you have colloidal particles, biological cells, and so on. You don't see much. Now, one way, the simplest way to see something is not to let your light go directly in the objective, but use what is called dark field microscopy. And sometimes it's also called ultramicroscopy in some applications, where actually the illumination comes from very strongly from the sides of the sample. So if this is your objective, no light is going to go in the objective from the one that used to illuminate. Only the light that is scattered from the object is going to be the one that you see. Sometimes you can also find microscope where the light comes from the sides of the objective itself. This is in reflected light. So this is the illuminating beam. And then you can see through the objective what scatters light. The point here is that that's what is called dark field. You can see that you don't see anything of the field itself. You only see the objects which appear bright. The difference between dark field and bright field, the bright field is the one where the light goes directly through. And you can see a bright field and you can eventually see the objects. This is, for example, how you can see something that is as delicate as DNA molecules. Just because they scatter light. Now, sometimes you can see objectives which are smaller than 100 nanometers. If you have metallic nanoparticles, they shine so bright that you can see metallic nanoparticles in this way. Now, however, what is the restriction of this method? You still have the restriction of the numerical aperture. You can see a 10 nanometer metallic particle, but usually the objective wouldn't allow you to resolve features which are smaller than 500 nanometers or so. So you don't know whether the bright dot that you see is one particle or two particles or five particles. So there are always, you can find clever people when they read about ultramicroscopy. They say, wow, I mean, you can see 10 nanometer features. Let's then go and take a look at this dense colloidal suspension of nanoparticles. I mean, good luck. I mean, you can't resolve them. You're going to see that they shine. On the other hand, however, if you have a single particle, you're going to see a single shining bright dot in your field. So it's useful. This is the simplest part of specialized microscopy. Yes?
Does it change the interpretation of what you see with the light coming from the sides?
Not really. I mean, you can, the interpretation should be made on the basis of scattering. So the intensity of the object depends on its scattering. And if you have, let's say, a soft shell which does not scatter, you may not see it. So you should always have in mind that what you see is what scatters light. If you have an object which does not scatter light, you're not going to see it. In terms of distance and scaling and so on, it does not change it. But in terms of scattering, I mean, like different objects appear differently. Now, the other type of microscopy, which is very simple to make, can be very powerful for some systems, is so-called polarized microscopy. Now, from physics, you know that you have a polarizer and analyzer. If you orient them in the same way, light goes through. But if you cross them, then the light will not go through, because the light which goes through this to the polarizer is not going to go through the second polarizer, which allows light polarized in the other direction to go through, but not light in this direction. The equivalent is that if you rotate them 90 degrees, no light is going to go through the set of polarizer and analyzer. Now, however, if you have a sample which has optical anisotropicity, like liquid crystal or fiber, the light which goes through the polarizer is going to be the polarization of light is going to get changed by this object because it polarizes light itself. So then you have the light going through the polarizer, being rotated a little bit, and this light is going to go through the analyzer. So the light through the background is not going to go through, but the light through the object is going to go through. And you can immediately see what you can do with just this simple combination. This is a nylon fiber. When nylon fibers are made, they are extruded, so the molecules are oriented in the same direction, more or less, and which makes them polarizing. The same is with paper, actually. When trees make fibers, they make the fibers, the starch takes specific orientation. Now, if you take a look on a bright field, I mean, besides being blinded, you can see maybe the outline of the fiber, but not that well. However, when you have cross polarizers, you don't see anything of the dark side, and you can immediately see the fiber itself, or you can change the different conditions and you can see the fiber as dark object or as bright object and so on. The point is that you immediately visualize objects with polarized light. This is very useful if you are synthesizing different chemicals and you want to check out whether you have a crystal or not. A crystal is a strong polarizer, and the non-crystalline material is not at all. So any, let's say, powder which appears bright is crystalline powder, and vice versa. Okay. Phase contrast. Now this is a little bit difficult to understand. It's a very powerful technique which we have on our microscope. If you can split the beam in two going through the sample, kind of you have a reference beam which goes through an outside area, and you have the beam going through the sample. When you discuss the film, we discuss that the phase when it goes through the material changes. In a very similar way in which you can see thin films having different colors, you can visualize the difference in the phase of the beam which goes through the sample. So if you have something which is equivalent of a thin film in the sample, it's going to get visualized. I mean, if you just go through a thin film, like you don't see the film, right? But if you kind of like check the light which goes through the film and the separate light, you are going to find out that they are a little bit different in phase. This is realized in the microscope in a way about which you don't even care, but it allows you to immediately, instead of seeing this uniformly bright field, if you do phase contrast microscopy, you immediately see any objects which have different optical thickness, like biological cells here. It's a very fast way to immediately get contrast in a sample which is transparent, just because you have the equivalent of thin films in the sample. Again, this is realized. I mean, you just have to pick the right objective and the right illuminator and so on, and they have this phase contrast feature built in. I mean, they just split the beam and make the contrast. But it's a powerful, easy to use feature. It can give you lots of quantitative information, but you cannot derive it in a usual microscope. There is a special interference microscope where you can actually measure thickness and so on by the interference method. Now, something that you should definitely know is fluorescence microscopy. A sample which shines. Again, the key here is how to make the sample shine, but the background not. In this case, what you do, you illuminate the sample with one wavelength, which is longer wavelength or shorter wavelength than the one that you see. Shorter, right. You illuminate with shorter wavelength. You have the fluorescent compound in the sample. This is what it looks. Shorter wavelength is the one that the compound absorbs. It converts the light from shorter wavelength to longer wavelength, and then it emits it at longer wavelength. So you illuminate, for example, with blue light and you see green fluorescence. Can you do the opposite? Illuminate with green light and get blue fluorescence? No, why not?
Gaining energy.
Right. I mean, like it would be, if you can do that, I mean, you can gain energy, right? I mean, the smaller the wavelength, the higher the energy of the light. There are optical devices which can do that, but actually they take 2 photons and convert it into 1 with higher energy. Now then you have the filter. If you have a filter here which transmits only the light and which illuminate, and you have another filter which cuts off this light but lets only the other light go through, then what you're going to see your bright object on a dark background just because it emits light. Extremely powerful technique, easy to use, a bit more difficult in terms of you have to take care with UV light sources, but apart from that, I mean, it's very powerful. And it is also the source of confocal scanning microscopy. I have this cute movie here, it's a little bit fast. Now, you want to increase your resolution. You want to have your sample, you want to see your sample in 3 dimensions. How do you do that with optical microscopy? What you can do is you can put an aperture here, and you can kind of scan the sample at a single spot at a time. So instead of shining all this light which gets scattered and so on, you can kind of in a way probe the sample one specific, very tightly focused spot at a time.
What's the light source?
The light source is typically a laser. This is how it works. I mean, you have a light source, illumination, laser. You have a very strongly focused beam. It scans the sample. In this case, you have this pinhole here. So you can scan by moving the pinhole. In reality, actually, what happens is the laser light goes through these 2 mirrors, which kind of scan the sample in around. Then it gets reflected back, and then it hits photomultipliers. You may have different photomultipliers for different wavelengths. But this technique allows you to resolve the structure of your sample with higher resolution than the resolution of the objective. And it allows you, when you do scanning in 3 dimensions, it allows you to actually scan your sample 3-dimensionally. So you can reconstruct the sample in 3 dimensions. And I'm actually, okay, any questions here? I'm going to show a couple of visualizations on my microscope obtained by my students.
What is the depth resolution of the different planes that you can use?
The depth can be as high as, let's say, 50 nanometers or so.
What is the lower limit?
That would
The
be
50 is the lower, right?
Yeah, that would be about lower limit. It's maybe much higher than optical microscopy. The depth of resolution of optical microscopy is very low. The light goes through. So it increases the depth of resolution very much. It increases the resolution itself a little bit, about a factor of 2. But what's most important, I mean, you can really need to resolve the objects at very, very high resolution and in 3 dimensions.
It doesn't look like it's very high resolution.
Which one?
When I look at those pictures, for example.
Well, because I mean we haven't really worked with high resolution. I mean, like we use very low resolution objectives because that's what we're interested in. And let me show you some examples of our data. This is supposed to be a movie. I don't know whether it's going to start ever or not. Somehow it wouldn't play on that computer. Okay, I'll show you the movie afterwards. Now this is a movie actually of a 3-dimensionally cross-section droplet, so you can rotate the droplet and you can see the particles inside the droplet.
So you could get a lot higher resolution if you're willing to use the
Sure.
this space to store it.
Well, I mean, but this is a relatively large droplet. You cannot see the whole droplet with a very large resolution. You can see only part of the droplet. And then this resolution in vertical direction, you can actually see how the droplet has, and you can see how the droplet shape, and you can see the particles. If you just use a regular UV microscope, you don't see anything. You see a milky droplet, right? Here you can see where the particles are. This is an image of 1 micrometer particles. Now the green particles are positively charged and the red particles are negatively charged. So when they were mixed, they coagulated. Now these are 1 micrometer particles, and by usual optical microscopy you're not going to see much and almost nothing at this resolution because this is a very low resolution objective. The scanner allows you to actually see those particles at high resolution and see which particle is which. So you can see the 3-dimensional aggregate. or I'm going to show you the three-dimensional image of the droplets when you drop by my office or when we finish the lecture here. Now the question is, how do we go to the next slide? Now I have put in a couple of slides here about transmission electron microscopy, which works similar to optical microscopy, but uses electrons. Now you can either go through a very thin sample, this is transmission microscopy at very high resolution, or you can do scanning on the surface at a relatively lower resolution. The disadvantage is that you have to work in vacuum and you have to have conductive samples, or you have to coat your samples with a conductive material. And the final slide here is just a comparison between different types of microscopy and the highest resolution that you can get and so on. I would like to ask to answer one or two questions and we're done.
How do you get those different colors in confocal microscopy, green and red for positive and negatively charged particles?
Confocal, because
fluorescence.
Two different photos.
right, you actually get the images with different filters, and you have the particles are green and red fluorescent. You have two different filters. So when you put the filter which allows only the red light to go through, you can see the red particles. When you put the filter which allows the green light to go through, you can see the green particles. And you can actually do this simultaneously and superimpose the images in real time.
Okay, so those have fluorescence in them.
Yeah.
Okay.
In confocal microscopy, typically you would like to use fluorescence microscopy. So it's usually a combination between the two. Okay, let's finish formally. Time is up. And if you get any questions, drop by.